Welcome back to the classroom. My name is Mr. Wong. I'm going to be continuing on Module 6, which is electromagnetism, where we're covering our first inquiry question, how charged particles interact in electric fields and magnetic fields, also charged conductors. Today's lesson will be focusing on charged particles in uniform magnetic fields. So we want to investigate the interaction, and we're going to try and derive a couple of relationships. One, the direction that charged particle moves relative to the magnetic field, and then two, what factors affect the magnitude of the magnetic force on that charged particle. Textbook references if you need. Okay, so this is the dot point we're looking at. We're going to look into what this equation actually means, and then we'll go further on to talk about a thing called the right-hand palm rule. Now, when I say right-hand palm rule, you might recognize the name as being something quite familiar, that being the right-hand grip rule. So a while ago in Module 4, we actually talked about how a current-carrying wire or a current-carrying wire as a solenoid, which is just curled wires, they can generate magnetic fields so long as you have an electric current running through it. So if I have an electric current running through here, then we have a magnetic field generated going this anti-clockwise direction. If we're looking at a straight line, your thumb represents the positive charge and your fingers represent the motion of the magnetic field. If we're looking at a solenoid, the direction of your fingers will tell you the direction of the positive charge or the motion of the positive charge, and then direction of the North Pole is your thumb, and then the back of your hand will be the South Pole. So we're now going to look at this in a different way. Instead of looking at how electric current generates the magnetic field, we're going to look at how what would happen if we apply an external magnetic field on this current here. So what I have here is an image of a cathode ray tube. Now a cathode ray tube is made up of electrons. Okay, so this is what we call a cathode ray tube, and it's firing out cathode rays, which are actually electrons. So we already talked about it. If we have a charged particle moving, so electrons moving along, these electrons are generating their own magnetic field. What you see here is I have a bar magnet. Okay, this bar magnet is projecting its magnetic fields onto this particular cathode ray. Now you can see there is a change in motion, meaning by we're experiencing a force, this being the magnetic force applied by this magnet's magnetic field and interacting with the magnetic field of our charged particle. So that gives us this kind of motion that we see here. What you can actually see is or if you can imagine, the magnetic field that's being applied. The magnetic field applied is going into the page like so. All right. But the direction or the force being acted on our electrons is actually going upwards like so. So if you can actually picture it on a side-on view, this is what I am sort of seeing. I see the magnetic fields coming directly horizontal, and I'm seeing the force or the direction that's being placed on the electrons acting perpendicular to that direction. Okay, so magnetic field, force, or magnetic force are perpendicular. And if you actually have a look, the charge is actually going, if you imagine, coming out the page at you like that. So each one is actually perpendicular to each other in this scenario, or simplistically speaking. Okay, so that's the behavior we're seeing in this animation. Let's look at other things. All right, we have two other scenarios to look at, two animations. One we're going to look at is what if the charged particle isn't moving? So over on this image on the left, the charged particle is stationary. Let's have a look at what motion we see later on. And then in our second scenario, this one over here, you can see this little black line that's showing the velocity vector. So this charged particle is moving, but it's moving parallel to our to our magnetic field. Now notice in our previous image, we said that this motion of the charged particle occurred because the lines or the magnetic field lines were perpendicular to the moving charged particle. But if we have a look here, you can see the charged particle, there's no deviation in its motion. So if there's no deviation in its motion, then there can't be an acceleration. So no change in direction would imply no acceleration. And by that, we have no force acting on our charged particle. So in this scenario here, the charged particle doesn't have a force acting on it. So no magnetic force. On this side here, when we have a zero velocity, we can also see the position or the motion of the charged particle hasn't changed. If there's no change in motion, Newton already told us, that means there's no external force being applied. So no external, in this case, magnetic force is being applied onto our object here. Okay, so those are a couple of key pointers to take note of. Okay, so we talked about how the current moves relative to the force, relative to the magnetic field. Let's do this again with this image here. So instead of looking at just a charged particle, let's look at current carrying conductors. Essentially, if we have a wire and we have electricity running through it, then we have a current carrying conductor. Okay, so anything that carries, or we can say electricity running through it. Okay, that's what we can look at. So in this case here, we have a charged particle, positive charge. So positive charge is going in this direction here. We have a magnetic field from north to south. So it's going from north to south like so. If you actually can picture it, our magnetic field, again, is perpendicular to our moving charge. Okay, so that's what we're seeing here. The force is being bent, if you can sort of imagine, out of the page or coming towards you. Okay, there's an actual way we can actually predict where each component is, so long as we know the other two information, and that's known as the right-hand palm rule. The right-hand palm rule states your thumb, your right thumb that is the direction of the positive charge. Your palm is the direction of the force that the positive charge experiences due to the magnetic field that it's run into. And then your fingers is the direction of where the magnetic field is going. Remember, the magnetic field is always going from north to south, so that's showing you that north to south direction there. Okay, just a nice little diagram for you to take into picture. So just remember your right thumb, direction of the positive current or positive charge. Your direction of the magnetic field is given by your fingers. Magnetic field is represented by a quantity known as capital B. And then the direction of the force out of the page. I like to always think of it as, Star Wars Yoda. but you might have a different way of remembering it. Okay, so let's go through a simple explanation. We have a cathode ray. This is an electron, so it has a negative charge. It will come in handy when we talk about this. It has a beam that strikes the point of the screen, producing a bright spot. Okay. The north end of a magnet is brought towards the beam as shown. Towards which point does the bright spot move? So before I go into this question, why don't we try and draw out the magnetic fields? So it's going from north to south. So our magnetic field kind of looks like this. So if it's going from north, it's coming out the page or towards the left-hand side like this. And then we have our charge. Okay, so I'm going to draw out a couple of things. We have our negative charge here. Okay, let's draw out my approach using my right-hand palm rule. Okay, so the north pole is going towards the left. So your fingers, your right hand fingers, should be pointing to the left like so. Okay, so there you go. The next bit is to then work out the direction that your thumb needs to be pointing. Now this one is a little bit trickier. So your right thumb depicts the direction of a positive charge. But in this question, we're dealing with a negative charge, which means, if we actually think about it, in the motion of electricity, if electrons are going in this direction, the positive charges left behind by the movement of the electrons is actually going in the opposite direction. That's how electricity actually works. It's the movement of charge. Okay, so if the electrons are actually moving out of the page or towards you, facing you, then that means your positive charges is actually going into the page. So your right thumb should be pointing in to the page that we have here. So if you flatten that out, right finger or your right hand fingers pointing to the left, right thumb pointing into the page. If you look at where your palm is at this current point in time, it's actually moving up. So it's going up the page, which means we'll see the electron move to position A. And A is the correct answer for this question. All right, so we go to the second multiple choice question. We have a beam of electrons moving straight through a region of magnetic fields coming out the page. So if you can imagine these dotted dots here, they're magnetic fields coming towards you. Okay. Which statement is correct about what we see in this diagram here? Now, before we go into the actual options, let's just try and work it out. We have an electric field that balances out the electric force, or the electrostatic force from this field is balancing out the magnetic force. So let's look at where the electric field is moving. And to do this, you can use your right hand palm rule. So because we're looking at a moving electron, the motion of our positive charge, or your right thumb, is actually pointing in the left-hand direction in this scenario here. Okay. Our magnetic field lines are coming out the page. Okay. So have your fingers pointing towards you. Okay. And your right thumb pointing to the right, or to the left, sorry. Your palm should be pushing upwards. In that case, you have a magnetic force pushing upwards. In that case, you'll have an electrostatic force to counter this going down in this direction. Notice how I drew the lines relatively similar in length to represent that they have similar magnitudes. So if that's the case, if it's going from top to bottom, that means this is our positive plate up here, and this is our negative plate down here. Okay, So let's look at what options we're dealing with. It says, which statement about this scenario is correct? The magnetic and electric fields are equal in strength. So this one's sort of a little misleading one. It doesn't necessarily mean that you have the same electric field strength. What's actually happening is the force is balancing each other out. So that's that there. The top electric plate is positively charged. Okay. So the correct answer that we have would actually be B. Okay. C, it's going in the opposite direction. And then the question for D, or the option D, it says the electric and magnetic fields cancel each other out. The force of the electric field and the magnetic field does, but not necessarily the field itself. The reason being why electric fields and magnetic fields can technically never cancel each other out is to cancel the fields out, because fields are vectors, they need to be moving parallel to each other. But if this is coming out the page and the electric field is coming down the page, the two fields are actually moving perpendicular to each other. So there's no way that the fields can actually cancel each other out. They're not even the same thing anyway, so you wouldn't be able to do such a thing. All right, so the next thing we want to look at is using this simulator that we have here, links below. What factors will influence the magnitude of the magnetic force on a charged particle going through a magnetic field? Okay, so the next thing we want to show is how does the charge of the particle, the magnetic field strength, how does changing that change our force acting on our object? We already know that in order for the charged particle to experience a magnetic force, it must be moving and it must be perpendicular, or it can't be parallel. The motion cannot be parallel to the magnetic field as it moves. So let's try and change the charge and the magnetic field strength and see what outcome we get. So this is our baseline motion. You can see it has a radius of 1 millimeter. Let's try and increase the magnetic field to 10. Let's see what happens to our charged particle. So it goes through here, and we get a bigger curve. So what you can see here is the amount of force experienced by this charged particle with a greater magnetic field strength is greater than what we had in our baseline. So what we could say is the magnetic force on the charged particle is directly proportional to the magnetic field strength. We can confirm that with the radius. The next thing we're going to do is to look at the charge, but to ensure this is a valid prediction of, or valid modeling of the relationship, we need to put that down. And then the charge, whoops, disappeared, come back. Okay, now we're going to increase the charge on the particle, and let's see what happens to the trajectory here. Okay, so not quite as strong as the magnetic force or magnetic field strength, but you can see still the amount of force this charged particle experienced was larger than our original baseline, which means both the charge of the particle and the magnetic field strength the particle is going through directly relates to the amount of force it experiences by the external magnetic field. Okay. Another interesting point that we'll talk about later is we can see it's a very clear semicircle motion here. So what's actually happening is when a charged particle goes through a magnetic field, it's actually undergoing circular motion. Okay, so let's have a look at some other examples. Okay, so let's do a quick summary of what we saw from that simulator. We know that the force on a charged particle or the magnetic force on a charged particle is directly proportional to the magnetic field strength it's traveling through. It is also directly proportional to the charge of the particle. And we already talked about previously, if the charge is not moving, then there is no magnetic force placed onto it. So the velocity on the charge also is directly proportional to the amount of force that will be used to keep it moving, like so in the magnetic field. We also stated that if the object was parallel, if the charged particle was parallel to the magnetic field, it would experience no force. However, in the examples we've looked at, the charged particle has gone perpendicular to the field. So if it's perpendicular to the field, we actually get maximum magnetic force, and if it's parallel, we get zero force. So there's a nice little relationship we can use, and we can use the trigonometry relationship of sine theta. The reason being, theta is the angle that the charge, moving charge, makes to the magnetic field. So in position where it's 90 degrees here, okay, we get a maximum magnetic force. If it's parallel, so if the magnetic field is going in this direction and the velocity is going in this direction, then there is no magnetic force experienced by a charged particle. So sine theta is the best one to use, because when sine 90 is 1, when sine is 0 is 0. And so this comes with our formula for the force on a charged particle. We call it 𝑞𝑣𝐵, or for those in Australia, we call that the Queen Victoria Building, 𝑞𝑣𝐵 sine theta. Okay, so this is the formula that we use to express the force exerted onto a charged particle in when traveling through an external magnetic field. Okay, so the last part of this theory component, we'll actually talk about the circular motion component of these charged particles. Since we're going to probably go over time in this video recording, I'm going to make a separate video to describe through this. So go to the prompts and you'll see the next part of this lesson.